Now I'd like to introduce Emmett Nelson. Emmett is going to talk to us about Helius MCT, which can be used for composite damage analysis. Emmett is the Chief Operating Officer at Firehole Technologies, and he's going to present, like I said, their new toolkit, which works alongside Abaqus and with Abaqus. So Emmett, I'm going to hand control over to you, and you can talk to us about Helius MCT.
To realistically simulate failure in a composite structure, two things must be captured: the progressive nature of composite failure and interactions at the micro scale. When I was a structural analyst for a large defense contractor, we rarely used progressive failure analysis. This was because we didn't have time for progressive failure, we couldn't understand the adjustable parameters, we couldn't get a solution, or just plain couldn't trust the results. Leaders in the analysis community are now recognizing that to accurately predict composite failure, a multi-scale analysis is required. Dr. Stephen Tsai of Stanford, the originator of the widely used Tsai-Wu failure criteria, now teaches multi-scale analysis in his composite design course. This is Casper, composite adapter for shared payload rides. I'll tell you more about it later, but as you can see from my colleague standing next to it, it's a large composite space structure. So if you're modeling something this big, why do you care about micro-scale interactions? Well, when analysis happens here, but failure in a composite happens here, between the fiber and doing this, you can't capture the progressive nature of a composite failure. Here's a typical failure progression. You'd load your composite, and then a single microcrack would form. Continued loading, and more microcrack. This could be followed by fiber crushing. To predict a progression like this, you need to know what's happening at the micro scale. Here's a simple example of a unidirectional composite subjected to unconstrained cooling. Because it's unconstrained, the stress field in the lamina is exactly zero. But large compressive stresses develop in the fibers due to the negative CTE of the carbon, and to counteract this, large tensile stresses develop in the matrix. In fact, for this particular material, if you submerge it in liquid nitrogen, the matrix fails with no mechanical load. Similar results can be seen under mechanical loading. Here's another simple example. It's a unidirectional composite subjected to biaxial compression in the transverse direction. Notice that there's no load in the 1-1 direction, but a stress of 108 megapascals develops in the 1-1 direction of the fibers. That's almost half of what develops in the loaded direction. And in the matrix, a stress of 3/4 of the loaded direction stress develops in the unloaded direction. So from these simple examples, it's easy to see how neglecting these masked stresses could contribute to erroneous simulation results. Helius MCT is a multi-scale progressive failure simulation technology for general analysis of composite structures. During its development, we've worked to reduce many of the problems associated with both multi-scale and progressive failure analysis, creating a tool that you can use and understand. It works well for quasi-static problems where multi-axial and thermal-mechanical load states are present. Now I'm going to tell you about some of the features of Helius MCT. And to me, the most important feature is proven results. I wish I had time to get into all the details of the benchmarking we've done with Helius MCT, but we've only got 15 minutes here. On the chart here, I've got several plots from published examples of benchmarking, 2 worldwide failure exercises, publications in ICCM and AIAA, and several internal programs with the Air Force Research Lab. If you're interested, please check out this website, www.fireholetech.com/abaqus, and don't forget the last splash there, where we'll have several comparisons of Helius MCT posted for you to be able to download after the presentation. The next feature I'm going to talk about is that we require only standard composite inputs, only require standard composite material inputs. Of course, if you want want to do a multi-scale analysis, you need to know something about the properties at the microscale. Well, that's where Helius Material Manager comes in. It's a standalone desktop application, and it characterizes microscale interactions from standard composite lamina test data and micromechanics. This movie is going to show you how easy it is to use, and typically this process takes 5 minutes or less. You start by giving your material name, and that's how it'll be stored in your and then the lamina strengths. Next, you go to the constant tab. You choose your material type, whether it's a carbon or glass, and save the material to your library. The third feature I'm going to talk about is how Helius MCT seamlessly integrates into Abaqus. Here's a flow chart of a typical structural analysis process. Helius MCT alters this process in 3 places. The first step is to characterize your material using the Material Manager, which I just showed you. Then, during the model building process, you create your material using the Helius MCT plugin. And finally, at runtime, the Helius MCT solver add-in is called to define stiffnesses, stresses, and the failure state. This movie is going to show you how to use the Helius MCT plugin. At this point, we have geometry defined, and we're in the property module of Abaqus CAE. Instead of going to your Materials tab, you when you select your material, you can double check them. Select your units, fiber direction, analysis criteria, output request. Go ahead and define a section. Click OK, and the Helius MCT solver add-in is automatically called at runtime, so you don't have to do anything different there. The final feature I'm going to talk about is the intelligent discrete softening method.